We present affordance-guided reinforcement learning via visual prompting, a method leveraging rewards shaped by vision language models for online reinforcement learning. Recently, there is a growing adoption of large multimodal foundation models for robotics that can perform visual reasoning in physical contexts. However, these systems generate coarse robot motions for manipulation tasks that may not be robust to potential variations. In comparison, robots equipped with reinforcement learning have the potential to learn more robust skills solely from a reward signal. In this work, we propose and study rewards shaped by VLMs. We present key point-based affordance guidance for improvements, or KAGI, a method leveraging rewards shaped by VLMs for autonomous RL. More specifically, our method is as follows. In the first step, KAGI takes the first observation of the episode, which consists of a top-down and side view of the environment. Then SAM2 generates candidate affordance key points for the VLM to select from. We visually prompt the VLM to select the correct key points and generate a waypoint sequence. In the second step, KAGI computes rewards for each frame. At each time step, we compute dense reward with respect to the waypoint sequence and sparse reward derived from a success classifier. We combine these rewards to optimize an online RL policy for the given task. For our real robot experiments, we evaluate KAGI on cloth covering, almond sweeping, spatula pick place, and cube stacking. These tasks are suitable for autonomous RL as they have a forward and backward component. The forward and backward policy are separately learned and alternately practiced. For each task, we train the policy on 10 forward and 10 backward demos, 5 times less than recent autonomous RL pipelines. We compare KAGI to an offline RL policy as well as RoboFume, which performs online fine-tuning using only sparse task completion rewards. For the cloth covering task, the offline RL policy is occasionally successful but sometimes struggles even with grasping. RoboFume improves after fine-tuning with sparse rewards but also does not lift the cloth high enough, knocking into the block and dropping the cloth. KAGI learned to uncover the block successfully with behavior shaped using dense rewards from VLM-generated waypoints. Though it sometimes releases prematurely, its qualitative behavior matches the demos most closely. For the almond sweeping task, the offline RL policy sometimes succeeds but also fails to sweep. RoboFume shows better performance, though it often misses several almonds. KAGI learned to sweep all the almonds to the right, occasionally demonstrating retry behavior. Though it sometimes misses a few almonds, its qualitative behavior is the best. For the spatula pick place task, the offline RL policy and RoboFume both struggled with grasp and precise placements. KAGI learned to place a spatula successfully, thanks to our dense rewards. Despite sometimes overshooting the placement, KAGI's behavior best matches the demos. For the cube stacking task, both offline RL and RoboFume struggled with grasping and precisely placing the cube. KAGI learned to stack the cubes, aided by the VLM-generated waypoints. Its behavior is best in picking and gently dropping the cube. We compared to Mocha, which executes actions planned by a VLM zero-shot, to understand if online fine-tuning offers any advantages. With precise resets closely matching the VLM inputs, Mocha is very successful. However, without them, performance drops noticeably. Even with very slight environment perturbations, Mocha's open-loop system fails to adapt. KAGI learns closed-loop policies robust to similar perturbations that are common in autonomous RL. Therefore, closed-loop RL policies fine-tuned with dense rewards are more generalizable and robust to environment changes than open-loop systems using hand-designed action primitives. Thank you.